Good morning, dear colleagues. And today our Vietnam colleague, Nguyen Trung, will present a report exploring defect structure in proton-implanted bismuth vanadium, a case study approach combining ab-initio calculations with positron spectroscopy. Please, Trung, you can start your report.
Okay. Just test. Sorry. First of all, thank for our college from Vietnamese college and foreigner college, Russian and Bulgaria and South Africa also. So today I would like to talk about my current topic about bismuth vanadate implantation. First of all, I would like to thank to JINR, Joint Institute for Nuclear Physics, and Institute of Physics, my institute, and Center of Nuclear Technology in Ho Chi Minh City, who provide some very deep insight, scientific supervisor, and Houston University and USDAT, who's the team which create material for us. So the title today, as you can see there, I will talk about the explosion defect structure in phosphorus implant bismuth vanadate. And it's the case study approach combined theoretical calculation with positron spectroscopy. So this report will present a comprehensive study on defect structure. That's been the full spectrum of bismuth vanadate. And after phosphorus ion implantation from accelerator in Poland. So this case study achieved two significant breakthrough. The first, we first time successfully applied the depth-dependent electron momentum distribution analysis at JINR. And second, we simultaneously combination of various variable energy positron measurement with theoretical TCDFT calculation and our experiment. So this study become from case study to become the standard methodology that we apply to our research group since 3 years. So this is the outline of my topic today. The first is motivation, the second is research methodology, result, and finally summary and conclusions. So for motivation, we know that nowadays we care about the energy, and nowadays people want to have more clean energy demand. So bismuth vanadate is one of promising for PSC material. PSC material, this is electrochemical cell. That device can convert us from solar energy from sun directly to the chemical energy. That means hydrogen here through water splitting. So its application is for clean hydrogen production, energy storage, and renewable energy conversion. So bismuth vanadate is one of promising material for this technique, for this technology, with a small band gap. That means it's available for the visible light here. That means the sunlight. And the chemical stability in aqueous environment. And this is potentially commercial for solar hydrogen because it's very cheap. But it still has the drawback. It has the high some property inside, like electron hold recombination rates or poor electron mobilization or short carrier lifetime. So we need to address the limitation. So this the case challenge here. We need to address it by modification material. So we use ion implantation modification here, because the conventional method just create defect usually on the surface layer. So the new ion implantation can create atomic scale defect to improve its photocatalytic performance. That means we can create control defect engineer. So then we choose the phosphorus ion at 100 kV because we see the stop range is just from the surface to 100 nanometer from surface, because you know that the water splitting just reaction just on the surface and on that very near surface region. And the phosphorus has similar electronic configuration. That means it can't replace vanadium in crystal lattice of bismuth vanadate, because this has the vanadium here. And it can create a new electronic state, and you know that we implant phosphorus, and phosphorus is one of the very common elements that are available in accelerator in Poland. So this is critical research gap. The phosphorus bismuth vanadate system lattice is a novel material combination, and there's a very limited research about this system. So this system is expected to enhance photocatalytic property through defect engineering. However, traditional methods like XRD, X-ray diffraction, STEM, or SPS have the limitation of point defect analysis. They just can't see on the surface only. We cannot see the deep inside of material. So then we need sensitive method to characterize the defect structure at atomic level, and need to understand the physical mechanism of property to enhance this. So our approach, we use positron spectroscopy. So why? Because you know that material have natural defect. So what is defect? Defect is like, So what is defect? Defect is like when you have the perfect lattice, so you have no defect. But when you remove one atom, it becomes monovacancy. When you remove two atoms, so it becomes d-vacancy. So you remove more than two atoms in the structure, it becomes the vacancy cluster, and it can become the void or other vacancy here. So this defect is potential positron trap. Why? Because positron is, when you miss an atom, that means you're missing the positive cause in the structure. That means you reduce the column repulsion. That means when the positron comes, it lack of repulsion to push the positron goes away. So that means the positron right now is trapping at the vacancy site. And different defect will have different positron behavior. So by recording positron annihilation radiation signal, we can get defect information and electronic property. Let's see the positron behavior in material. The first, when positron come into material, so it will lose energy from high energy to thermal energy. We call it thermalization. And then it will diffusion in material and annihilation. And with the perfect lattice, it will annihilate with the bow electron here. But when you have defect, like monovacancy here, that means you lack of the positive core. So the positron will come and stay there. We call it positron get trapped by vacancy defect. So the second, we see that positron spectroscopy is quite sensitive to defect. That means the positron can trap at the vacancy site, and we can see the atomic scale defect. And we can detect with the ppm level. That means it's ultra low detection, and this method is non-destructive method. We can get electronic environment with Doppler broadening, And with momentum distribution analysis, we can see the atomic species identification at the defect site. So why positron beam? With the use of positron beam, we can control the energy, positron energy from 0.1 to 30 keV. That means you can control the depth of positron inside material from surface and up to 2,000 nanometer of depth. And you can estimate the layer thickness. For example, you have, for some semiconductor, you have multi-layer. So you can estimate which layer of semiconductor. And the last region is the quantitative. That's it, two main parameters, S and the gap parameter for defect characterization. I will talk briefly about this. So with our solution approach, we used a comprehensive strategy for ion implantation. We can create the defect through anti-beam, not just surface compared to other conventional methods. And the second here, we use variable positron beam at positron facility at Dubna. So that means we have the depth result defect characterization. And we use the phosphorus ion implantation from various fluents here. And we use the updated calculation from experiment, theoretical calculation and experiment to see to have the complete atomic level understanding. And finally, we use other nuclear analytical methods like XRDSM, TEM, IBS to support our results. So the innovation here, we for successfully application of we call it variable energy electron momentum distribution. That means VE-AMD analysis. And the first comprehensive study with the defect induced by phosphorus inside bismuth vanadate. And with this novel combination, we built the methodology that apply as the standard approach at our group. So I will talk very briefly what do we measure actually. So when you know that the positron is the antiparticle of electron, and positron come to when it interact with positron and electron, it will emit 2 gamma, and we measure this gamma. Different electronic environment will have different gamma peak shape. This is one of the peak shape. So we have 2 parameters. The first parameter is S, the formula here. The S parameter will see the valence electron inside material. That means defect indicator. And increase of S, that means increase of concentration of vacancy. And the V parameter is mean the high momentum of the core electron inside material. It can show us the chemical environment surrounds and annihilation region.
What's W stand for?
W stands for the high. No, this is the tail. W is the tail here. W is the tail, and the tail is, you know, this is the peak of annihilation peak here. So W stands for very high momentum on of core electron inside. So we had the challenging when we built the method to analyze its electron momentum distribution. The problem here, the raw spectrum contains multiple components, like you have gamma light. This is true event. You have small content scattering. This is background contribution. You have incompletely charged collection from detector. You have the pi-up effect. So we actually need to extract the pure gamma light. That's mean this one. So solution here, we use the HMA method. HMA method, I mean, they call it a high momentum analysis to subtract the background Doppler for single detector. So let's see a little bit about the normal gamma peak. The component is here. The gamma line small angle scattering in reality is like this, incompletely charged, so it should be like this. And the pi-up effect here. So that means the two gamma event is the convoluted a lot of at least four components here. So HMA method was proposed by Hawk 2006. They used a mathematical formula to describe the component, and its component is described by a parameter here. Then we just need to subtract everything here by a code or something you can code. And then you just need to extract the two gamma event here. That's mean here. So after subtraction in their study, it should look like this. So we're still concerning about this material and about this method. And we have tested to our silicon. So this is the raw spectrum of annihilation on the spectrum component. Then I subtract everything there, and it becomes like this. So the final count is in green. And you see here, it's a better solution compared to the raw spectrum. So our concerning has been confirmed that we are doing the right way. Why? Because for the first time at JINR on January this year, we have the coincident Doppler. And then we use the silicon background subtract by HMA method. And then we compare together them in the same light. And this is the ratio of two methods subtract to the coincident Doppler. So you can see that the subtract method for single detector show quite good agreement in the low momentum here, and the semi-core, I called it the middle momentum, and that means the valence and semi-core electron, that means below than 25. And from 25, it's a little bit noisy because we cannot measure a lot of count there due to the limitation of technology right now. So that means our method for single detector is quite good. It's confirmed the HMA method is quite accurate. What does it mean? It means that we can have the clean gamma annihilation spectra, and we will have more accurate SVK parameter for defect characterization, and we will enhance defect sensitivity from the noise here. And for the Bismuth Verde, it should look like this. And the electron momentum distribution is, you take the ratio of the sample to the reference, and the reference we choose here is the perfect lattice of silicon. It look like this. And this peak will have information of defect inside material. So this is the first approach from experiment method. And the second approach, we use theoretical approach. Theoretical approach, we use relaxation of the lattice because the old model cannot explain the structural distortion from defect. The distortion can be explained here. For example, when you miss an atom here, the structure is not straight anymore. It distorts. It's like expand or destroy a little bit. And then, for example, when you replace one atom or you replace two, so you see that the structural lattice right now It's not normal anymore compared to this one. So the old model cannot explain this. But our modern model can take into account relaxation of defect and also the force from electron and positrons. So the result from theoretical calculation here, we will have the more accurate positron lifetime and Doppler spectra electron momentum distribution. So we need to compare about between experiment and theoretical. First is positron lifetime, but it's not available for the thin film. The second is the web fit to estimate the positron diffusion length in material. And finally, and the first fingerprint here is advocate parameter I just mentioned about. And the final is momentum distribution. This is the first and second fingerprint. So from the web fit, with the outcome here, we can estimate the thickness of multilayer or block or region inside the thin film. And we can see the positron diffusion length. So there's some prediction from very first web fit result. And then it was confirmed by other positron method. I will skip it very fastly because it's quite detailed. And for theoretical results, in this study, we need to simulate 17 cage that defect that we think that it in reality. So from theoretical, we can see the SVK parameter also, and we can have theoretical electron momentum distribution. That means we can see the behavior of positron in the defect structure. And this is one of our work. That means we will simulate this kind of lattice. And illustration of positron inside material look like this. It's in the yellow. This is the location of positron in the mono vacancy of red. That means oxygen here. In theoretical, it will look like this. And the final result, we can get the theoretical Doppler spectra. So for the first finger, we need to compare between experiment and simulation. I call this is like defect map by depth, because we take the region of from this range and this range, and we see that it's quite near to the calculation result, experiment near to calculation result. And we confirm some prediction from the web fit result. So the second fingerprint here, we collect the momentum distribution from theoretical and experiment also. It will show the environment surround defect. And you see that for the first time, we detect phosphorus by the peak at 7. But other method cannot detect. And we can see again the high sensitivity of positron method. So I will summarize the key finding here. We see the atomic level of depth-dependent evolution. This is very detailed here, so I do not want to mention here. We split it by region of the thin film from the surface to the 225 nanometer of depth. So the question here right now, after defect identification, what is the role of defect by modification to material property? So we need to build, after this, we need to build the relationship of observed defect from positron and this material. So we connect to other chemical group to see that our defect can improve some property like less electron hole loss or more time for photocatalytic reaction or higher quantum efficient. And for absorption, we see that it can generate more charge carrier and utilize more visible light or more efficient with the sunlight. And it reduces the band gap. That means it's easier to excitation under the sun light. So in the overall, that means from three property, we think that our defect, our modification by implantation, it can enhance photocatalytic performance of this material. So finally, I want to talk about the significant finding and impact in this study. So we first provide comprehensive reviewing defect structure in bismuth vanadium by ion implantation, and it can enhance the new defect that control defect engineering by ion implantation technology. In future application, we hope that it can improve the photocatalysis for clean energy and can be used for commercial hydrogen storage. To conclude, our study, this study becomes the case study to standard methodology that I apply to our group, because we first time successful depth-dependent EMD analysis for single detector. And it's the experiment and theoretical dual approach. And second, we provide valuable insight of modern past technique for defect characterization. And this methodology is now applied for various material I showed here. In future plans, so maybe we don't need to use substrate method anymore, because we have the constant Doppler by Roblin isocyclic. So with this result, we submit it on the American Chemical Society in the round number 2. So hopefully it can be published. Thank you. If you have any question, please.
Thank you, Chun. Are you going to use 2 germanium detector for this analysis also?
Yes, thank you so much.
You're going to.
That means thank you so much for your question. We are right now. Okay, let me show here. We are right now analyzing very first spectrum of the second detector. That means constant. We have constant detector right now, but we still need to optimize result. And with the silicon here, you see that this is very first result for the constant Doppler. And our method here is quite similar. So.
It means that you use just only one spectrum from one detector.
Yes, that's right. For background subtracted, just one detector. But you know that it heavily depends on mathematical model. So
What do you mean mathematical model?
it's like this.
The function.
The function.
So I saw many parameters in this function. It's so good to get a stable solution if you use some fitting code.
So that's why. So that's why we just can describe for the violent.
From my point of view, if I use a function, fitting function with about 10 parameters,
10
so it's
parameter.
not, for example, 10 parameter, let's say, and the solution is not so stable. It depends very much on conditions you are up, the initial conditions for each parameters.
That's right, and in material is also depend on material also, and we can see that it's not correctly 100%. It just can describe from this one is near an annihilation peak here. So we just can describe from this. We cannot describe for subtraction from very high momentum there. That means the tail. That means we just can describe from the, how to say this, the S only. And a little bit intermediate momentum there. But in the high momentum, it's unpredictable.
What's the reason where you choose phosphor ion for implantation?
Okay, for the region we used for the phosphor implantation, first because phosphor has similar electronic configuration to replace vanadium. And we hope that after ion implantation, so phosphor can create some kind of defect that increase material property. And from engineer, from technology, you know that it's just one of common element that available in Poland. So
it means that in Poland you can use only phosphor ion.
No, because for elite element.
Is it possible to implant in Russia? In Moscow, for example?
Actually, in our JINR, we do not have
low
energy.
It's very difficult to lower energy of ion beam.
Yes, that's right.
Instead of China, is there anywhere in Russia you can use? Because every time you have to move the sample to Marie Curie Institute in Poland, it's not so easy.
It's not so easy. It takes 2 years for ion implantation and transfer sample to our group. It takes 2.5 years.
So with the help of Dr. Kulik?
That's right. Because I have no idea about low energy ion implantation in Russia. So maybe we must ask our colleague.
I see. I also to characterize the material after implantation. Could you use neutron diffraction?
For neutron diffraction, because when we do this study, the IBR is temporary shut down. So at that time we cannot use
now
it.
Now it's started working. So you can use it.
In the future we can.
Okay, if you want to use neutron diffraction, so please ask me. I can help you.
Thank you so much.
And another question is DFT calculation for you use software or you develop by yourself?
We use the package that called ab-initio. It's free sources. This is a free sources package.
Okay.
And you know that because it's free sources, so it have a lot of limitation. So the develop there not yet improved 100%.
Thank you.
Thank you. More questions, please.
I have a very simple question, but I don't understand that. You use a positron to detect the defect in the material, right?
Yeah, that's right.
And your method is can detect how many defects in the material, or can be observe the position of the defects in the material.
Yeah, that's right. Let's see briefly. Let's figure out the final summary defect. In very detailed, we can see from surface we split into the region. The first region does mean near surface region. From 0 to 30 nanometer, we see the amorphization phase, and it's confirmed by other methods. And we see the competition between other defects inside in this layer. And in the second layer, we see the higher concentration of phosphorus because we detect phosphorus here. And then we see the complex defect cluster like this. And we see the interstitial of phosphorus into bismuth vanadate. And finally, we again see the complex defect at high fluent. That means it's in the higher fluent. And we see the stop range of the phenomena of phosphorus EN at 200 nanometer. So this conclusion is quite in the good agreement with other methods. It support, it's like the cross check, and it support each other. So by positron, by theoretical, we see very detailed defect point.
Yes, thank you.
Thank you. More questions, please.
Thank you for your presentation. I have two questions for you. The first question is how to preserve the integrity of the sample. So in this experiment, you use the ion beam to irradiate the sample.
Yep.
And as I see, the sample can be applied in many applications. So it means you need to preserve the sample, not to be damaged by the ion beam. So I would like to ask how to preserve the integrity of a sample.
Okay. Let's see a little bit about what we do here. So this is from laboratory thin film. Positron is non-destructive. But the way why we implant this, because we want to create defect. We want to create a defect. And this defect can optimize the electronic property. And this enhancement of electronic property or optical property can help to increase the catalytic performance.
Yeah, I understand that, but I mean the threshold of the dose transfer to the sample. It means you irradiate the very long time, very long time, and then the sample is completely damaged.
Before this, we actually failed in some experiments, and this is one of experiments that's successful. We failed like 2 sets of sample because some physical conditions, too much overheat. We have too much currencies in the ion implanter also. So this is the third set that successful. So yeah, before that after this we used the another set that in the different physical condition also, and it's successful also. Yeah.
Okay, thank you. And my second question is, it's very interesting that after the sample is defected, and then the electrical and optical property of the sample is enhanced and applied in many applications. And I saw that you examined the optical absorption of the sample. You show the graph that show the absorption of the sample.
Yeah, let's see a little bit, because this work is actually from the mechanical team.
Maybe the next slide.
Okay, the next slide.
Yeah, this one. So I wonder that the sample is solid. And it's literally it is a sharp all the line passing to it. So I wonder that how you measure this data.
From that this is the thin film, and this is
film.
Yeah, this is the thin film. Yeah, this is the thin film. So it has the surface, and we measure this thin film. Yeah.
It means the light can penetrate through the thin film.
That's right.
Okay.
This is the thin film.
Yeah, thank you.
From very initial, we I'm not sure it can work here. Okay. From very initial, we have the material here. This is bismuth vanadium thin film. Yeah.
I saw that it is a solid sample, but actually it is a thin film.
Yeah, it's
Okay.
like a thin film. 1 micrometer thin film.
I also have another question.
Yes.
Before implantation, how you design the time for implantation? What kind of software?
Before this, actually, we just simulated by stream to estimate the depth and the energy. But you know that in reality, we failed 2 times because at that time we didn't expect about the heating. That means, how to say this? The temperature of the sample and the temperature during implantation. So we failed 2 times actually.
Okay, thanks again for your nice report,
Yes,
answers. Thank you, Chu.
yes, thank you so much.